key statistical software. He has played a crucial role in public inquiries on medical statistics, including the British heart surgery scandal and the Shipman case. A passionate advocate for statistical literacy, and he has engaged the public through his BBC documentary. So I would invite everyone to look at Tales You Win. His risky talks on podcasts and numerous media appearances made him very, very special. He served as the president of the Royal Statistical Institute and is widely recognized for his contribution to evidence-based decision making. Professor Spiegelhalter is a fellow of the Royal Society and has received numerous accolades, which is very difficult, almost impossible for everyone to cover in this short time, including the Guy Medal in gold and a knighthood in 2014. And he is entitled with the accolade of Sir from the Britain government. So we are so proud to have you here, Professor Spiegelhalter. Over to you now.
Well, thank you very much indeed. There's an overwhelming welcome, I think, that I find really quite difficult to follow. But I'm really pleased to have this invitation to talk to Lums, and yeah, I'm going to try out some material on you and see how it works. I think I'll talk for about, I don't know, 35 minutes or so, and then I want to open up for questions, which can be on any topic you like about communicating statistics. Can someone mute themselves? Okay, and so that's I'm really looking forward to doing that. Okay, so that was me. Hang on, can everyone?
Reza, can you mute?
Can you mute yourself, please? No. Can you move? Oh, great. Okay. So, as Imran said, I used to do clever, difficult stuff in statistical methodology, and and you write stuff on uncertainty in AI and Bayesian clinical trials and Bayesian computation, which I spent a lot of time on, and was really good. I enjoyed doing that, and it was important stuff. But actually, by 2007 or so, I got a bit bored with doing all this sort of academic stuff, and I was really lucky to be philanthropically funded by a very rich hedge fund man who which allowed me to go into communication of statistics and risk and just work in a sort of more public sphere, public facing. And so I started making TV programs on climate change, and I made programs on probability and risk, and did game shows jumping over the big red bulls in Argentina, ridiculous things. And for those of you who know, one of the biggest accolades in the UK is appearing on Desert Island Discs, which is a strange radio program in which you say what 8 records you would take with you if you were stranded on a desert island. And this was an absolute peak achievement. I think because I did a lot of work during COVID, explaining the statistics of the pandemic to the public, which was appreciated. Okay, so that's what I've done, and I've written some books. Art of Statistics has sold very well, and this is my new book, and I'm going to be talking about the things I'm talking about today are all in this book. And as you can see from the topics, a lot comes under the art of uncertainty. There's certainly probability theory, which I will be talking about, but all sorts of other aspects, which I won't have time to talk about today, to do with the confidence in statistical modelling, in making predictions, in risk communication, and so on. But today I'm going to be mainly talking about luck, randomness, what is probability, and coincidences. So the first topics in the book. So, as I said, what is uncertainty? And what is it? And the definition I like is extremely personal. It's the conscious awareness of ignorance. So it's not saying that uncertainty is a property of the world. Maybe everything in the world is predestined, but we don't know. So we have uncertainty about what is going on, we have uncertainty about many things, about what's going to happen in the future, what's happening at the moment, and why things happen. So there is so much we are uncertain about in our lives. And so what I emphasize in the book is that it's a relationship between a subject who is uncertain, you, me, well, I am uncertain, and an object, something I'm uncertain about. So it's a relationship, and we need to think of it in that way. And but uncertainty can be chance. So I've got a coin here, and I might say to you, what's the probability this will come up on the UK on the head side with the Queen or King's head? And what if I flip it? What's the probability of it come up heads? And usually people will say 50-50 or 50% probability. And we're talking there about what in English we might call chance, what we can't know, some property of the world. But then if I flip it and cover it up, I could ask you, what's the probability or your probability that this is heads? And I can look at it myself. So I know what it is, but what is your probability? Now, this has changed and event with an audience, I won't do it now, but people might, are really a bit unhappy about it. But in the end, they will say, "Oh, all right, 50%. And they don't like doing it usually, but they will actually say that. And because it's changed completely what I'm talking about. I'm talking about what's known as epistemic uncertainty, about our ignorance and what we don't know. And the whole perspective in the book, what I would call a Bayesian perspective, is that it's quite reasonable to put probabilities on what we don't know. And I shall prove it to you in a moment when I give you a little quiz. So I think this is quite reasonable to do this. And this book is about what I call about deconstructing uncertainty. It's about sort of how to think slowly about our ignorance, about not knowing. Probability is a part of that, but only one part. There's a lot more besides. So that's what I talk about. Now, I I like numbers, and so I want people to put their probabilities, their uncertainty into numbers. So, because in our daily language, in English, we would use words like perhaps or maybe, or this could happen, or this might happen. And every language has got its own words for your personal uncertainty about what you don't know. But words can be very dangerous indeed because people interpret them in very different ways. So I give my example in the book about the Bay of Pigs. Now, you may not know about this. This was in 1959. There was a revolution in Cuba, and Fidel Castro took power, and the CIA in America wanted to depose Castro, and they planned an invasion by 1,500 Cuban exiles at the Bay of Pigs to happen in 1961. Um, and But it was secret. Even the U.S. Army didn't know. The president did, but who was Eisenhower at the time. And then when President Kennedy became inaugurated in 1961, he found out about this plan. He didn't know before, and he commissioned the intelligence report by the Joint Chiefs of Staff to see who didn't know about it, to think what to suggest whether this was a good idea, and they didn't think it was a good idea. They thought there was about a 30% chance of success, 70% chance of failure. That was their assessment when they thought about it in numbers. Unfortunately, by the time the report went to Kennedy, they had taken the numbers out and replaced them by words, the phrase a fair chance of success. Now, I think, you know, if you want know even a little English, you'll know that that actually, might sound quite good. But they meant it's not very good chance of success, but people would interpret that as a reasonable chance of success. Anyway, Kennedy approved the invasion, not just because of this report, but it certainly didn't help stop it. And it was a complete disaster, absolute disaster. That's Castro jumping off a tank. All the exiles were captured or killed. It was a total disaster. And afterwards, there were a lot of reports and recriminations about why didn't anyone tell Kennedy what a bad idea this was. Now, since then, people have learnt how that we should try to put our uncertainty into numbers because words are easily misunderstood. So, and this is done within climate change and within many areas that words are given numerical definitions. So now in the UK intelligence services, if I worked for MI5 or MI6, that's where James Bond works for, and I use the word likely, I have to mean between 55% and 75% probability. And I know this because here it is, I got a mug. I gave a talk at MI5 to the intelligence services, and they gave me a mug. And on it, they show the translation of how likely I am to need a refill of coffee. So you can see that if it's 55 to 75% empty, I'm likely to need a refill. But what that shows clearly that if you thought there was a 30% chance of anything, you have to use the word unlikely, which is what they would have used in the Bay of Pigs example. And so it's unfortunate that there wasn't this kind of scale available then. Now, the next example I realize is very difficult and contentious in Pakistan because it concerns, and I'm very aware of that, the suggestion that Osama bin Laden was in a compound in Abbottabad, and the Americans were deciding whether to send in the Navy SEALs, of course, without telling Pakistan about it, to actually try to kill Osama bin Laden. So this is 50 years later, and things had changed in the US. Now Obama had multiple teams working on assessing a probability that bin Laden was in the compound. And President Obama later said some teams thought it was only a 30 to 40% chance. Others thought it was as high as 80 to 90%. So a lot of differences in opinions. The 30 to 40% may have been what's called a red team, a group of people or an individual who's specifically trying to find problems, very pessimistic, looking what could go wrong. And that's very useful. So he had a broad range of opinion, a long discussion, and he then thought, well, basically it's 50-50, and he approved the raid. Now, after that, it's been argued about whether those intelligence teams should have got together to come up with a single joint assessment. And I would say no, that when you're assessing probabilities, it's very good to know about the range of opinion, the differences in opinion between people. Okay, so probability. I mean, what is it? What is it? We use it all the time. We use it in gambling. Well, some people who do gamble, and of course, not everybody does. Risk analysis. We use it in insurance, in modeling, when we calculate confidence intervals or Bayesian credible intervals. We use it in science. We calculate p-values. We do all this sort of stuff, and it's all based on probability. But what does it mean? What are probabilities? What is it? Now, are the probabilities we assess, we calculate, are they estimates of some true underlying probability or a propensity or some sort of frequency, which is the sort of classical view? I mean, but on the other hand, where is probability? You can't grasp it. You can't measure it. You can't see it. It's not like time or distance or heat or any of these things. You can't sort of directly measure it. So does it actually even exist? Or did we just make the idea up? Now, I am quite my personal opinions are quite extreme on this, and I'm not saying this is the only way to think about it, but my personal opinions is that probability doesn't exist. And I wrote a paper in Nature at the end of last year, which got quite a lot of interest, saying, does probability exist? And I said,
Professor,
probably not.
Professor,
Yeah.
sorry for interrupting you. There is a question in the chat box.
Okay.
How having range of opinions is better than unifying them?
Oh, I see. Okay, I'll come back to that. Yeah, because for the decision maker, he needs to know the source of uncertainty. And some of that uncertainty is within team or within model uncertainty, but it's also important to know about disagreement between different models or different experts. So that's why I think that it's very good to have multiple statistical models, multiple analyses, so that the decision maker who has to take responsibility can see how much disagreement there is, because that is a major source of his uncertainty or her uncertainty. Okay, good question. Thank you. So I said but it's useful to act as if it does. So because I believe that all numerical probabilities are constructs based on judgments and assumptions. For example, before I flip the coin, you might have said a 50-50 chance of a head. But if I show you this carefully, I don't know if you can see, it's a two-tailed coin. It's the same on both sides. So this is a very illegal £2 piece from the UK, specially made to be the same on both sides. So your assumptions that I was honest and trustworthy were wrong. I was being dishonest. I didn't say it was a fair coin. I just said it was a coin. So I wasn't lying. So the point is that it shows that it's all based on your assumptions, any probability. And I believe they're essentially subjective. But we can check how good they are, as I'll show in a moment, using this idea of scoring rules. And I do believe there are some chances out there in the world, proper, true probabilities, when we're talking about gas molecules or lotteries or things like that. The irony is that these are actually deterministic systems. They're actually not stochastic, really. They've got probability distributions, but they are just complex deterministic situations with very strong symmetries. They're essentially chaotic. And so I believe that probability distributions arise much more from chaos than from genuine randomness. Maybe the quantum world is different. Not my job. It's all very strange anyway. But even there, maybe probabilities really do exist in the quantum world. But even there, many people argue that any numerical probability distribution is relative to the observer rather than just being a property of the particle itself. But that's beyond my expertise. Okay, now I want you to look at your probabilities. I want you to quantify your ignorance. So I'm going to give you a little quiz. I'm going to give you as 5 questions, and there's a true answer, either A or B. And you've got to say, which I hope you don't know the answer. These are difficult questions, mainly. Not all. They are difficult questions. And then you've got to think of how confident you are about your answer and score your confidence between 5 and 10. If you're absolutely sure, say 10 out of 10. If you've no idea, say 5 out of 10. And in between, you can pay 6, 7, 8, 9, 10. And then you score yourself when you get the correct answer. And this is the scoring rule. It's a really powerful, beautiful scoring rule. So what you see then, if you say 10 out of 10 for 10 out of 10, you're confident. If you're right, you get 25 points. And if you're wrong, you lose 75 points. So it's a really hard teacher, really punishing teacher. It's asymmetric. If you say 7 out of 10 confidence, if you're right, you get 16. If you're wrong, you lose 24. So I'm sure you can keep track of this yourself. And I'd like to see if you know can spot the pattern to these numbers. Okay, first question. Okay, Lahore is known as the Paris of the East, but which has got the biggest population, according to Wikipedia, using the UN 2018? Lahore or Paris? Which has got the biggest population? Now, according to the UN figures for 2018 on Wikipedia. So you have to know, which one do you prefer, and then how confident are you about your answer? So have you done that in your mind? And the answer is, hang on. The answer is Lahore. Not by much. According to this, 11,700,000 for Lahore, 10,900,000 for Paris, according to this index. So if you said 10 out of 10 on Paris, you've got off to a really bad start. Now, maybe you knew that and you scored 25 points, which is good. Okay, next question. Who is older, Donald Trump or Xi Jinping, the president of China, president of States, US, or president of China? Who is older? Okay. And you've got to state your answers, how confident you are. And the answer for that one is A. I think I might be a bit easy. That one. Donald Trump is quite a lot older. He's 79, is he? No, 70, what's that? 78. 78. And Xi Jinping is he's a bit older, 2 months older than me, Xi Jinping, born 1953. So that might be a bit easy. Let's have another one. Which is further east, Lahore or Mumbai? Which is further east, Lahore or Mumbai? And no looking on your phones, no cheating. Okay. And the answer is Lahore is further east, just a little bit further east. Mumbai shifted on the west coast of India, a little bit further west. Okay. So which is bigger, Venus or Earth as planets? You might know. If not, you have to sort of guess. And the answer is Earth. Earth is a bit bigger than Venus. Not much, but a little bit. And then finally, which is the biggest area in square kilometers, Pakistan or Nigeria? Now, I personally would find that very difficult, but maybe you know. Which is the biggest area, Pakistan or Nigeria? And the answer is Nigeria is slightly bigger than Pakistan. Not by much, slightly bigger. So I hope you found those difficult. And I hope, if you were a live audience in front of me, I'd ask, how many people got lots of points, and I'd also ask how many people ended up with negative points. And lots of people, people do get, especially with general audiences, the majority end up with negative points because they say 10 out of 10 and they're wrong and they just lose 75, and then it's really difficult to catch up. So and because you can, if you get negative points, you could always have done better just by saying 5 every single time. So someone who's really ignorant would have done even better. So the point about this is a quiz, but actually it's quite a serious issue. And these sorts of quizzes are used to train people to be probability assessors. What I hope I've convinced you is that you can construct your own probabilities for your own beliefs in facts. Now, what's the pattern of the scoring rule? It's beautiful. What you want to do to spot the pattern is look at the maximum you can score as 25. So look at the loss that you have by not getting 25. In other words, subtract 25 from all of those. And then you get -1, working from the top, -1, -4, -9, -16, -25, -36, -49, etc. which is the squares. You lose the square of your error. This is just squared error loss, which was developed for weather forecasting, probabilities of rain, in 1950. It's really powerful. It's the scoring rule that's still used for weather forecasting, and it's also used for super forecasting competitions, training forecasters to be good. So it's a really powerful idea. Okay, so I'd like to just talk a little bit about luck. Um, I'm fascinated by luck. I don't believe luck is, you know, an external force, but people do say, "Oh, I was lucky," or "Someone was lucky." It's things that are unpredictable and they're not in your control, but they have an impact. But lots of people talk, "Oh, that was really unlucky," or "That was lucky," or so on. I use as an example my grandfather. There's my grandfather, 109 years ago in 1916 in the First World War in the army, and he got in 1918 he had, I think, about the worst job you could have, a brigade gas officer in the Ypres salient, which is one of the worst parts of the war. That's what it looked like where he was working, inspecting the gas, the gas anti-gas installations. A really dangerous job, shells coming over all the time, and he kept a diary, which we've got, which is a treasure, a real personal treasure that we got, his diary. And he records, he says, desolation, lucky to get through in time, narrow escape. It was a really dangerous job at the beginning of 1918. And he lasted 3 weeks in the job, which I think was quite good. 3 weeks. And then he got blown up. A shell came over, exploded close to him, but it didn't kill him. So was he lucky or unlucky? And it's a good example of looking at types of luck. And there's philosophers have identified 3 types of luck, which I think are important. The first one is constitutive luck, who you were born as. Just who, in what period of who your parents were, what period of history you were born into, what class you were born into, where was the country at war, etc., etc. What were your genes? What was all your early upbringing? All these things you had no control over, and yet are incredibly important for the future. And my grandfather had, I think, bad constitutive luck of being born into the generation that was sent to the First World War. Then there's circumstantial luck, just being at the right place at the right time, or the wrong place at the wrong time, meeting an important person, just by chance, or being, as my grandfather was, having that terrible job and being at a certain place when a shell came over and blew him up. But the final bit of luck is outcome luck. How events just happen to have worked out for you at that particular time. And for him, it was incredibly lucky, because he was taken out of frontline actions, and so he was behind the front lines in the terrible battles that followed, and so he survived them, which I don't think he would have, and that's why I'm here, because I wouldn't be here if he hadn't survived. So I find this really, and he lived till he was 81, as my grandfather. So constitutive luck is extraordinary because it's who you were born as. And if you think of constitutive luck, it's about making the best of the hand you've been dealt. It's how it's known. It's also a Western phrase, making it like it's like a game of cards or something. Make the best of the hand you've been dealt, because you can't do anything about who you were born as. You're stuck with it. So you just try to make the best of it. And I think this is a really good analogy, for those who play cards, because you are unique genetically, and just as every shuffle, every hand you can be dealt when you play cards is, I do a pack of cards, I've shuffled them up, and I can do that again, is almost certainly unique. Because, and you may have heard this before, I can be really confident that nobody in the whole history of humanity and every card game that's ever been played has ever had the cards in that order. And I shuffle that again. And I can be really confident that nobody has ever had the cards in that order before. This is a unique order of cards. Now, that's quite a big claim, and of course I can't logically know that, but probabilistically I can be very sure by counting the number of shuffles. So now we come to a bit of maths. The first card, of course, can be any one of 52, and the second one can be any one of 51, and the second one can be either 50, and so on. And we get to 52 factorial. And 52 factorial is a big number. And I always say, well, if you tried, putting it into your phone, you'd run out of numbers, the space for the numbers, and after a while your phone might explode, although I don't think it would. So it's a big number. Actually, it's quite bigger than that, and it's and lo, it is a very big number. Oh, it's bigger than that. Bigger. Oh, I forgot some zeros. So it's that big. That's what 52 factorial is. It's about the same as the number of atoms in our galaxy, the number of shuffles you can do. And so we can calculate that if everybody who had ever lived on Earth had done nothing in their life except shuffle cards and present hands, the chance that two of them would ever have had the same shuffle is incredibly low. It's about 10 to the minus 19, which is, about the chance of, is less than the chance of me guessing two cell phone numbers and getting them exactly right first time, which is pretty well, is very small indeed. So, and I find that is really unintuitive, quite extraordinary. So, but when we talk about extraordinary events happening, I'd like to show you a video. This is somebody, Derren Brown, who's a British performer, sort of magician, and he said he could take a real coin, not like this, a real coin, and flip it and get heads 10 times in a row. And I'm going to try showing this video, and can you tell me if the sound doesn't work?
10 heads in a row. Watch. One. That's heads. Two. That's heads.
No. Oh, sorry. I made a mess there. Oh no, what have I done? What have I done? What have I done? Sorry, I pushed the wrong button. Okay. No, what a mess. Hang on, hang on. I tried to be clever. No. Okay. I'll be there in a minute. Oh, what a mess. I'm sorry. I do apologize. What a shambles. Hang on. I'll be there in just a moment. Yeah. I'll move it on a bit.
Heads. Heads, that is 4. Heads, 5. Six. 4 more to go, and I'll stop. 7. 3 more. 8. 9 heads. Last one. 10. 10 heads in a row. Thank you very much indeed.
Okay, so he flipped 10 heads in a row, and normally with an audience, I'd ask, well, how did he do it? Was he lucky or unlucky to flip 10 heads in a row? And people would say, how did he do it? How did he do it? And, and it was a real coin, and he really did. It wasn't cut, the filming. He really did flip 10 heads in a row like that. But, of course, now we reveal how he actually did it.
10 heads in a row. Watch. To predict a run of 10 heads in a row and then make it happen is hugely unlikely. The chance of it happening is about 1 in 1,000.
1 in 1,000.
However, if you flip a coin thousands of times and record the results, somewhere along that line of heads and tails, a line of 10 heads is actually very likely to appear. Okay, 10 heads in a row. That's 1. To work out the system, you need to understand that we can only know what comes from our own limited experience. And our experience can often be very far from the truth. I can't see the bowl anymore. Here we go. 10. What you saw was the final minute of what was an excruciatingly long day. We filmed for over 9 hours until eventually a clear run of heads appeared. 9 heads. Last one. The impossible became inevitable. 10. 10 heads in a row. Thank you very much indeed.
So he took 9 hours standing, very professional to do that, and keep a look each time as if he was doing it the first time to get 10 heads in a row. So was he unlucky or lucky to take 9 hours? Was he unlucky to take that long? Would you have expected him to do it before that? And we can do some maths for this. The probability that you succeed at each attempt before you get a tail is 1 in 1,000, as you said, a half times a half times a half, 10 times. So on average, we expect to take 1,000 attempts, an average, but there's a lot of variation around that. And I reckon he took around 1,600 attempts. It's about 3,500 flips he had to do in order to take 9 hours. So I think he was unlucky to take so long, to take 9 hours. And my colleague, James Grime, did it and it only took him an hour. He did it in an hour. It's all on YouTube. It's a very boring YouTube video, but he stood there and he repeated that performance, but he did it, only took an hour to do it. Now, how long do we have to wait for the first success? And this is introduction to the geometric distribution. If the probability of getting success at any attempt is P is 1 in 1,000, then the probability of success the first attempt is P. The probability of the second attempt is the probability of failing of the first attempt, which is 1 minus P, times P, which is the probability of succeeding at the second attempt, etc., etc. And we get then the probability that the first success at the nth attempt is 1 minus P to the n minus 1 times P. And when we draw that out, that's the picture we get. It's a geometric distribution. Really beautiful. The most likely time for the first success is the very first throw. And we can see that Derren Brown was near the tail of that distribution, whereas James Grime, my friend, was at the beginning of that distribution. So sometimes we can put probabilities on how lucky or unlucky somebody has been. That brings us on to coincidences. What is a coincidence? And I quite like, the two statisticians got a nice definition for a coincidence. They said a surprising concurrence of events perceived as meaningfully related with no apparent causal connection. So something that just happens, you have no idea why. Well, that's a coincidence. I met somebody when I was away somewhere, I met a friend or something like that. So why do they happen? Sorry?
There is a question, is luck relative then?
Is luck what? Sorry?
Relative.
Relative. Yeah, well, I don't think luck really exists as an outside force. I think it's just something we label for things that happen. It's a useful word for things that happened to us that were important, but over which we had no control and which were unpredictable. So I don't think it's not out there. It's not out there. It's just something it's a label we give, I think. Yeah. Right. So coincidences, they don't happen to me very much because to have coincidence, you have to talk to people and notice things. And I don't talk to people very much, and I walk around like that. So they don't happen to me very much. Except they did happen once. I bought a box of 6 eggs and they all had double yolks. So I cracked them open. There they all are. 6 double yolked eggs. So And that was amazing because, you know, sometimes this gets in a newspaper when someone gets 6 double yolks in a box. Um, and there's a man who says only 1 in 1,000 eggs are double yolked. So they say the chance of 6 eggs is 1 in 1,000 times 1 in 1,000, 1 in a million, 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 million. Oh, I don't know, 1 in a million, million, million. What's wrong with this? Well, it's just wrong. And I'll tell you why in a moment. Okay. So, the point is, I'm sure you all know about birthday matches, about where you get coincidences happen more often than we think they should. Because if you've got 23 people, and I would, with an audience, I can do this, it's very nice. If you've got 23 people and you ask them the last 2 digits of their cell phone numbers, there's a 94% probability that at least 2 will have the same last 2 digits. It's a really good, works nearly every time, almost every time. 20 people, it's an 85% chance. So it's a really good thing to do with an audience. If you've got 20 people, it's very likely that 2 of them will have matching last 2 figures. Birthdays, 51% probability of at least 1 match. So, you know, half the time, if you've got 23 people, there'll be 2 people with the same birthday. And even if they haven't got the same birthday, a 77% probability of an adjacent birthday, the same or an adjacent birthday. So 23 people is a good number to try coincidences on. The point is randomness, assuming these things are just chance variation, is clumpy. It's not equally spread out. And how do I get to that 51%? If I'm teaching this, I'd say, well, you got 23 people in a row. The first has got some birthday. The probability that the second has got a new birthday, a different birthday, is 364 over 365. The probability the third has got a new birthday is 363 over 365. So the probability the 23rd has got a new birthday is that. So the probability they've all got different birthdays is that all multiplied up together, which gets to less than a half. And the paradox, the unintuitiveness comes, I think, because all those numbers are near 1, are big numbers, but when you multiply them together, the product goes down below a half, because then the probability there's at least 1 match is 1 minus that is 0.51. So that means in any group of 23 people, 50%, 51% chance that 2 people will share the same birthday. And the usual way to illustrate that is that in any football match, there's 23 people on the pitch, the 2 teams and the referee. So in half of all football matches, 2 people on the pitch have got the same birthday. And people prove that all the time. But a nice example was in the Women's World Cup, because in the World Cup, each squad has got 23 members. Isn't that great? They got 23 members in every World Cup. I don't know why. Reserves, I suppose. Anyway, they've all got 23 members. So we would expect half the teams to have a pair. And in fact, out of the 32 squads, 17 had at least 1 pair with a matching birthday. And Brazil, Colombia, and Denmark had 2 pairs of shared birthdays, and Morocco and Nigeria had 3 pairs. And there's a lovely example for Morocco, for New Zealand, from Nigeria, where there are 2 people, a very Christian country, both born on Christmas Day, and they called them Christy and Glory were their names. So these coincidences happen far more often than we'd expect. So finally, how did I get 6 double yolked eggs? Well, I bought a box of double yolked eggs. You can go into a shop or online, sometimes, not all shops, sometimes, and just buy double yolked eggs. And you can get them online from Tesco's or something. You can buy double yolked eggs. So actually people can identify double yolked eggs and put them in a box, and sometimes they've got some left over and they put them in another box. So that's how you get double yolked eggs. Anyway, so I'm going to stop now and say good luck to everybody, whether you believe in luck or not. I wish you the best of fortune, and I'm going to stop showing my screen and be quiet. And oh, sorry, I've talked for too long. So I'm really sorry for talk for so long. I'm happy to try to answer some questions.
Okay, thank you so much, sir. Thank you. It was very, very interesting talk.
People put their points up. Someone got 55 points. That's fantastic. That's really good to get 55.
Yeah.
Oh, people have been putting their answers in the chat. You're not supposed to put your answers in the chat. Yeah.
Yeah.
Okay. Right. Okay.
Excellent.
So any
Imran, would you
questions?
like to say?
Sorry?
Imran?
Yeah, it was a very engaging and wonderful talk, Professor Spiegelhalter, and definitely it make a good case that people got some new keywords. And I believe I have seen your book in the bookstores in Pakistan, and I hope it will be a good invitation for the audience to go through those books. And you made a very good case to study those books, and particularly the way you introduced